Okay, so here's the first big equation that we need that's going to form the basis of everything else that we do. Okay? And that's F equals big G M1 M2 over distance squared. Okay? Sometimes you see it written as big G M1 M2 over R squared. Okay? The only difference is that if you just have like the distance between two objects and they're not in orbit, you use distance. If you're talking about something being in orbit as it goes around something else, then you're going to use R. Okay? It's mathematically the exact same. So historically what happened is that Isaac Newton comes up with this. So it's kind of like Avogadro's number, okay? Avogadro, if you remember Avogadro's number, anybody remember Avogadro's number?
6.02 times.
6.02 times 10 to the 23rd, number of atoms in 1 mole. He never actually came up with the number, okay? All he did was propose the idea. This is 1 mole of anything is going to contain a certain number of particles. He never actually came up with the number. He was just a big idea kind of guy. Same thing with Isaac Newton. Isaac Newton didn't actually come up with this value of G. Talk about a guy by the name of Henry Cavendish later on. He was the one that actually came up with the value. So this value of big G is called the universal gravitational constant. Okay? Let's talk about this. It's universal. That means if you're on Earth, if you're on Mars, if you're on Pluto, Neptune, wherever, doesn't matter. This number is not going to change. It's universal. Now, in contrast to that, we talk about little g. Okay? Little g is your gravitational acceleration. That changes. Little g is different on the Earth than it is on the Moon, which is different what it is on Mars. Okay? So little g is not a constant. The concept is there. Oh, I'm on Mars, I drop something, it's going to accelerate. I'm on the Moon, I drop something, it's going to accelerate. But that value changes based upon where you are in our solar system or where you are in the entire universe. Okay? This big G, as best we can tell, every place we've been able to measure it, has remained the same. Okay? So, if you look on the top left corner of your equation sheet, you have this value. It's 6.67 times 10 to the negative 11th newtons meter squared over second squared. Okay? Now, this is a number you are going to use a lot. And there's also numbers we're going to use a lot, the mass of the Earth and the radius of the Earth. I would recommend that you store this number in a memory cell of your calculator. You should have an STO button, okay, and then you can assign it to different variables. If you do that, do not type in times 10. We're going to be dealing with a bunch of exponents in this unit. Numbers that are exceptionally big, numbers that are exceptionally small. When you type this in, I would go 6.67 and then EE and then like negative 11. The EE takes the place of the times 10. If you punch in times 10, it tends to really screw up your order of operations, okay? So I would store that as 6.67 EE to the negative 11th. Now here's how you can check that you got it right. There should be an STO. I would store it as G. That would make sense, okay? So here's how you can get it right. There should also be like a recall button to get that variable back. So then if you take G and multiply it by 1, you should get an answer of 6.67 times 10 to the negative 11. That's the easiest way to check that you got it right. You don't have to store this. I would, because otherwise you're going to be punching this number in a lot. And this is just a more efficient way to handle that variable. Okay? Now, this is a very small number. So what Newton did, he goes, look, I just know this is a small number. I don't know what it is. I have other things to worry about, like inventing calculus. So generations of students are being tortured by trying to find the derivative of x squared. So, I want to leave this to someone else. Henry Cavendish came up with a number, we'll talk about that tomorrow. So, he just said, if I find the gravitational force between any two objects, there's only 3 criteria that you need to find the gravitational force between two objects. You need the mass of each object and how far apart they are. So what that means is that you are gravitationally attracted to, obviously, to the Earth. Okay, it's kind of this big rock that we're on. We're kind of attracted to it. You're also gravitationally attracted to the Moon, the Earth, Jupiter, Mars. You are gravitationally attracted to Proxima Centaurus, the next star closest to us. You are attracted to the Andromeda Galaxy, to the black hole at the center of the Andromeda Galaxy you are attracted to. You are attracted to the black hole at the center of our own Milky Way galaxy. So everybody says, oh, we're in zero gravity. Okay, let me explain the only way from a physics perspective you can be in zero gravity, and this is the ultimate freshman mentality. The only way that you can be in zero gravity if you are the only thing that exists in the universe. Like nothing else exists in the universe other than you. Okay? Because if there is mass anywhere else in the universe, even a single electron, somewhere else, you would be gravitationally attracted to this. So the idea of zero gravity only exists if there is only one thing in the universe that has mass, and that isn't it. Okay? So don't ever say, oh, we're in zero gravity. Not happening. Okay? Cannot happen. You are obviously gravitationally attracted to this rock that we're on. Okay, so give you an example of how this works. So Mara is sitting here, right? And there is a fire extinguisher over there on the wall. Okay? And we're going to make the math simple. So we're going to say that Mara has a mass of 50 kilograms. The fire extinguisher has a mass of 2 kilograms. And they are separated by a distance of 5 meters. Okay? So here's Mara, there's the fire extinguisher. It's about 5 meters away. I want to determine the gravitational force of attraction between Mara and the fire extinguisher. She has mass, the fire extinguisher has mass. We know the distance between them. Now, before we do this calculation, do you think we're going to get an answer that's really, really big or an answer that's really, really small? Small. There are a lot of things I worry about when I walk in this room when I start this lecture. One of the things I don't worry about is all of a sudden Mara and the fire extinguisher start, like closing rank and accelerating towards each other. Okay? If that happens, there's any number of weird things that are taking place, and the lecture isn't on the list of things I'm going to worry about at that point. Okay? So we're going to be able to calculate this value. All right? But you kind of know it's going to be a pretty small value. Now, here's the other thing. When on this unit, on gravity and motions of satellites, this unit has the potential for you to get answers that make absolutely no sense. Okay? I mean, like mathematically, they make no sense. So, for example, and even though you haven't learned this equation yet, let's just talk, see, you can get an idea. So when I drop an object right now on Earth, I get an acceleration of 9.8 meters per second squared. Okay? I drop this. Good. Boom. There's my acceleration. So imagine that I am out here, way out here, okay, about a third of the way between the Moon and the Earth. I'm way, 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 way out there, okay? I built this really, 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 really tall ladder that puts me about a third of the way between the Moon and the Earth, okay? I'm out here. I drop the same golf ball and it begins to fall, okay? Even though you haven't learned the equation yet, do you think the dropped ball, because it's that far away from the Earth, do you think the acceleration is going to be bigger or smaller than 9.8 meters per second squared?
Smaller.
Smaller. You were a long way, right? You were a long way away. I had students in my first block AP physics class who took the test today. They got an answer of 10 to the 14th meters per second squared. Swear to God. Okay? Even though I asked them, don't you think that should be less than 9.8? Yeah? Really? Half the class literally got an answer bigger than 9.8. So, because they punched numbers in wrong into the calculator, okay? They used the wrong radius. Okay? They understood the equations, they understood the concept, but they just made a mistake mathematically. One of the things you're going to do is you're going to calculate the orbital period for the Lunar Command Module as it orbits the moon on the Apollo missions. It should take about an hour and a half. Okay? So that's one of the things you do on the test. Promise me. The test, which is going to be next week, this is going to be one of the things you're going to do. You're going to calculate the orbital period of the Lunar Command Module as it orbits around the moon. It should take about an hour and a half. There's two extremes over the years that I've gotten for that answer. The smallest answer I ever got was 0.05 seconds. So it's like, you can't snap your fingers in 0.05 seconds. Okay? You need 0.05 seconds. Really? The other extreme answer, and I actually did the conversion because I was just out of curiosity. The other answer I got, which was in seconds, was literally longer than the universe itself has existed. Like it was longer than 14.7 billion years.
What did they do?
Literally. That was longer than the universe, our entire universe, not the Earth, okay? The universe has existed. Now you all sit there and you laugh and go, Mr. Burkamp, we'll never do anything like that. You lie?
I'll get you a more extreme one.
Okay? So that's what I'm telling you, because you're going to be dealing with really, really big numbers, because really, really big distances, and really big values of mass, and you're going to be squaring them, you're going to be cubing them, and you're going to be, all of this stuff. So be very skeptical of any answer you get from the oracle, okay? If your calculator ever rolls you under the bus, it will be this unit, okay? You will get answers that don't make any sense, but you're going to sit there and go, oh yeah, it takes 3.7 times 10 to the 18th seconds to orbit around the moon. Cool, okay? No, telling you. So, before you touch your calculator, we're going to get an idea of what we call an order of magnitude for this force between Mara and the fire extinguisher. Don't touch your calculators. Do not touch your calculators. I just want to get an idea of what the answer should be. So we have 6.67 times 10 to the negative 11th, and this has units of meters squared over kilograms squared. It looks weird, but it'll make sense in just a second. So then the mass of Mara is 50 kilograms. The mass of the fire extinguisher is 2 kilograms. And they're separated by a distance of 5 meters, but that's going to get squared. Okay? So, here's the story. Just order of magnitude. Order of magnitude, all you worry about is just the exponents. So 50 times 2 is 100. So that's 10 to the second. Okay? So it's 10 to the second. I take 10 to the second times 10 to the negative 11th, I get what? To the negative 9th, right? Okay, because I'm adding exponents, because I'm multiplying, right? So just as a ballpark, on the top, I'm going to get 10 to the negative 9th. Okay? Cool. I got 5 squared, which is 25. 25 is 10 to the first, right? 2.5 times 10 to the first. Okay? So when I take 10 to the negative 9th and divide it by 10 to the first, since I'm dividing, do I subtract the exponents or add the exponents?
Subtract.
So I take 10 to the negative 9th minus 1, I get 10 to the negative 10. That gives me a ballpark of what I should get. Okay? It's a ballpark. It might be 10 to the negative 9th. It might be 10 to the negative 11th, but it's going to be somewhere in this neighborhood. So if I do this calculation and I get 10 to the 4th, whoa, that's really, really bad, okay? Or if I get 10 to the negative 20th, ooh, that's even worse, okay? So make sure you know how to use your calculator. Do this calculation, somebody do this calculation, and let me know what you get.
2.67 times 10 to the negative 10.
What'd you get?
2.67 times 10 to the negative 10.
Times 10 to the negative 10. Cool. Now, let's look at the units that you get out of this. You have to pay attention to units. When we dealt with Kepler's third law, remember I said I don't care what the units are because it's a ratio? Okay, those days have passed, okay? Now you're back into newtons, which means you have to work off the MKS system, which is kilograms meters per second. That's the only thing you're allowed to work on, kilograms meters per second. So I take kilograms times kilograms, I get what?
Kilograms squared.
Kilograms squared. But then I'm dividing by kilograms squared, so all those kilograms go away. I've got meters squared on the bottom, I got meters squared on the top. Those all cancel out, I get
Newtons.
I just get newtons. So this is a measure of force, okay? So that's going to be newtons. So that's the value of the force, okay? Obviously, that's a very, 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 very small number. Can we calculate it? Yes. Does it matter? No, okay? It isn't like, you know, I see Mara starts to lean towards the fire extinguisher. So, oh man, I get tired of fighting the force. I'm going to lean this way, okay? Or her hair starts to drift out towards the fire extinguisher, okay? No. Is it there? Yes. Now, the only time this would ever be a factor is if Mara and the fire extinguisher sounds like the name of a band. Give it up for Mara and the fire extinguisher. So Mara's here, the fire extinguisher is over there. And they're in deep, 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 deep space. And those are the only two things. There would be a gravitational attraction in Mars and the fire extinguisher. And over a period of time, they would begin to drift towards each other. Okay? Now it isn't like bam, something like that, right? But they would begin to drift towards each other. Now, an interesting thing happens. So, we're going to take this distance from 5 meters to 2.5 meters. Okay? So Mara and the fire extinguisher have drifted towards each other, and the distance has shrunk to 2.5. Okay? So again, before you do any calculations at all, think this through. As Mara drifts towards the fire extinguisher, and they're closer, what's going to happen to the gravitational force? Will it increase or decrease? Increase what? Yeah, you're dividing by a smaller number. This is what's known as an inverse square relationship. Because you're dividing by distance squared, okay? So if the force becomes, or the distance becomes smaller, the force has to get bigger, right? So, the only thing that's going to change is the bottom number. We're not going to change the mass of Mara. We're not going to change the mass of the fire extinguisher. The only thing that's going to change is the distance. So, 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared, times the same 50 kilograms, times the same 2 kilograms, otherwise known as 100, and then divide that by 2.5 meters squared. So what'd you get out of that one?
1.07 times 10 to the negative 9.
Now, is it still a small number?
Yeah.
Yes. But now, let's make a comparison. So, 10 to the negative 9th, because it's a negative exponent, indicates that it's a bigger number than 10 to the negative 10th. So, Nathan, take that 1.07 times 10 to the negative 9th and divide that by the 2.67 times 10 to the negative 10th. I want to make a comparison between these two numbers.
4.
Oh, you get 4. Oh. Why'd you get 4?
Magic.
Magic?
You decrease the distance by a factor of 2, but distance is squared, which would be a factor of 4.
Beautiful. So, if you look at F equaling big G, M1, M2 over distance squared, Okay? Just start with that equation. So if I decrease the distance by 2, so my new force is going to be the same big G, M1, M2, but now I've got D over 2 squared, because that's what it means. I took the 5 meters, I divided it by 2, and I got 2.5. So it's just like what Jackson said. Now I've got M1, M2 over D squared over 4. Since I have D squared over 4, what's going to happen to the 4?
Pops up.
It pops up, it increases by a factor of 4. Okay? So this is why it's known as an inverse square relationship. Now, Mara's sitting there going, oh, that kind of freaks me out. I don't want to, no, this is bad. I don't want to feel the force of the fire extinguisher. So Mara, instead of walking towards the fire extinguisher, she goes, I'm out. Instead of being 5 meters away, she's going to move all the way over here to the corner, and now she's going to double the distance she's away from it to 10 meters. What's going to happen to the amount of gravitational force? Increase or decrease? Decrease. Why? She's further away. You double the distance. So look at this. If I double the distance, I have big G, M1, M2 over 2D squared. 2 squared is
4.
So if I double the distance, instead of being 4 times greater, it becomes 1/4 as much. If I triple the distance, what would happen to the force?
9.
Go down by a factor of 9. Okay? So if you look at a graph of gravitational force versus distance, what's the graph going to look like? Well, when you're close, you have a
Great force.
greater force. As the distance increases,
It look like a slide.
okay? Now, will that force between Mara and the fire extinguisher ever go to 0? No matter where Mara goes in the universe, she will always be gravitationally attracted to the fire extinguisher on that wall. Okay, it will never go to 0. Now, will it become an exponentially small number? Yes. Okay, even when she's in the room, it's 10 to the negative 9th. Okay, right? Not anything Mara's ever going to have to worry about. It's like, oh man, I feel the pull of that fire extinguisher. No, you don't. That's, the world is tilted. That's not right. Okay, so got that idea. All right, so here's what I need you to understand at this point. There's an inverse square relationship between distance and force. So now, we're not going to actually calculate the force between Mercury and the Sun. But what we're going to look at is how the force changes as it goes around in its orbit. So if you look at what we just talked about, and we said here was the Sun, here's Mercury. Okay? Allowing for the equation that we just established. When is Mercury going to have its strongest gravitational pull? Closest, further away?
Closest.
When it's closest. So at that single point, which you should have marked on your graph as the single point where Mercury is going fastest, that's when the gravitational force is going to be strongest. At the point when it's furthest away, the gravitational force is going to be its weakest. Okay? Now, at this point, we're not going to actually calculate the value of the force. All I want to do is try and figure out how does that force change as it goes around. Okay, that's all I want to do. I don't want to actually calculate the force. Listen to me. We are not doing the force calculations. We're just saying, hey, on a relative amount. So if Mara has a relative value of force of 1 between the fire extinguisher now, when she's closer and she cuts that distance to half, it would go up by a factor of 4. If she moves twice as far away, it would be 1/4 as much. Okay? That's all we're doing. We're not actually calculating the values of force. We're just seeing how it changes. Okay, so page 3. This is going to be the same for everybody. So on line 2, it says determine the distance from Mercury to the Sun when it's at its furthest point. So, you don't get to answer this. So, at what's the biggest radius that you have on that orbit? 0.467 AUs, okay? This is what we're gonna call D2, okay? This is not D squared, it's just D2. This is just some distance, okay? This happens to be the biggest distance. We're calling that D2, okay? No, going down. Now, D1 is at its closest point. So what's the smallest radius that you have? 0.307 AUs. So that's going to be D1. So here's what we're going to do. We're going to find the relative amount of force as it changes from going from its furthest point to its closest point. Okay? So down here on number 5, okay, this is where the magic is going to happen. We're going to find the ratio of the force when it's closest to the point when it has its furthest distance away. Now, technically, this should be big G, mass of Mercury, mass of the sun over distance when it's closest squared, divided by big G, mass of Mercury, mass of the sun over the distance when it's furthest away squared. Now, since we're doing a ratio, what happens to the big G, the mass of Mercury, and the mass of the sun?
Cancel out.
Those all cancel out because this is just a ratio. That's why I don't need the numbers at this point, okay? It's just a ratio. And it's a ratio of things that are inverses of each other and they're in the denominator. So here's what you're going to do. So this is why this works. So on number 5, I've given you this. 1 over D1 over D2 squared gives me the relative amount of force. Listen to me. This is not newtons. This is not the amount of force. All we're saying is that this is the relative amount of force, okay? So, we've got D1, which we said was 0.307 AUs. And then we have D2, which was 0.467 AUs. So somebody take the inverse of that, square it,
2.31.
2.31. Now, what units do you have at this point?
None.
Just not.
You have absolutely no units. What's the only units that existed?
AUs.
AUs, but those were divided out. So these are not newtons. Do not put newtons on the end of Mercamp. We've always talked about force measurement. Newton. This is not the force. You are not going to keep Mercury in orbit around the sun with 2.31 newtons of force. Okay? No. That's about how much force it takes to lift my remote control. No, I am not going to keep a planet in orbit around the sun with 2.31 newtons of force. All we're saying is that that force, when it's closest, is 2.31 times greater than when it's furthest away. Okay, that's all we're saying. It's just 2.31 times greater. So here's what you need to do. You're going to find that single point when it was furthest away. And you're going to draw a line 1 centimeter long pointing from the point when it's furthest away towards the sun. Because that's the direction of the force, because that's what we need to create centripetal force to keep Mercury in orbit as it goes around the sun. That's going to go 1 centimeter. Now, it would just muddy the waters, but I do want to point out one thing. Everybody has this idea that, Mercury is being pulled in a gravitational field towards the sun. And it is, I'm not disputing that. But to actually do this right, we should go to the sun and draw an equal vector pointing out this way. Because Newton's third law says what? For every action there is a
Equal and opposite reaction.
equal and opposite reaction. So if Mercury is being pulled with a relative force of 1, guess what?
Sun.
Sun is being pulled by Mercury with a relative value of 1. We're not going to draw it, but you need to understand that concept. Everybody goes, Mercury is pulled in its orbit. Yes, it is, but guess what? Mercury is pulling on the sun as well. Now, that's 1. Boom, 1 centimeter. Then you're gonna go to the point where Mercury is closest to its orbit, and then you're gonna draw a vector 2.31 centimeters long. Because what we're saying is that when Mercury is at its closest orbit, the relative value of the force is 2.31 times greater. Now to give you, let's put this in terms that you all can understand. Let's say that you make $10 an hour. You have a job and you make $10 an hour. You walk in today, the judge, or your boss says, you've been doing good work, working hard, taking physics. I'm gonna boost your salary by a factor of 2.31. Okay? It's kind of cool, because now you're gonna go from $10 an hour to what? $23.10 an hour. That's kind of a big deal, okay? Not only are you doubling the salary, it's like 2 1/3 your increase. That's pretty cool, okay? So, but this is what I want you to see, is that as Mercury is at its closest point, that force isn't just bigger, that force is 2.31 times, is more than double than what it is at its furthest point in that elliptical orbit, okay? So, that's going 1 through 5, that's going to be the same for everybody. Now what you need to do is that you're going to pick one point over here, one point on each side of the orbit, and you're going to calculate the relative value of that force at those points, okay? So, this is where everything's going to change because everybody's going to pick different numbers. So you're going to pick a D1. D2 is going to stay the same for everybody. D2 is our baseline because that's what we call 1. So you're going to pick a different D1 value. Okay, I don't care which point you pick. Pick one over here. You're going to pick a point, find that radius, divide it by D2, square it, take the inverse of it. Then you do the same thing at some point over here. So when you get done, I should be able to clearly see 4 arrows, okay? And the calculations that generate those other relative forces. I emphasize clearly see 4 arrows, okay? Don't draw them so faint that, oh, I can see them. No, Ken Burkamp see them at 11 o'clock tonight when I'm grading these, okay? That's how you want to view that. So when you get done with this orbital graph, you should have, not you, I should be able to clearly see the point where it's going fastest, the point where it's going slowest, the region where it's slowing down, the region where it's speeding up, and then 4 arrows that shows the relative force, okay? So if you're not sure you draw them clearly, hand it to the person next to you and go, hey, do you think Burkamp can see these? And if they go, that's bad, okay? If they don't emphatically say, oh yeah, Burkamp can see them, just let that be your bellwether. So, Bar, stop you on camera, do that part.